So you're here for the graph scale change theorem, lesson 3.5, right? I'm doing my civic duty and you're here in class. So I want to introduce you to what happens when you change the x part and the y part of an equation, what it's going to do to your graph, and vice versa when you change the graph, what it does to the equation. So there's both vertical scale changes and horizontal scale changes. We're going to stretch the graph horizontally sideways when we change the x values, and we're going to stretch and shrink the picture vertically when we change the y. In your book, we're going to start off with some basic shapes and graphs and whatnot. And we're going to start with this one here as an example. Actually, the one in blue there is x cubed minus 4x. And what we want to do is we want to see the effect when we change the equation, how that affects the graph. And we're going to look at both. And so I built another graph here it's got these sliders, okay? And that's represented by the red line. And what I've done is I've taken the equation x cubed minus 4, and to fiddle with the equation, I'm going to replace y with y over b and x with x over a. And that's going to have an effect on what the picture looks like. B will affect the vertical change in the picture, and A will affect the horizontal change in the picture. In fact, if we start with that, just fiddle around with this a little bit, work with the slider here. So I said that B changes something in the y direction. So I've got this little slider, and I can pull it, and I go. The number is getting bigger: 2.5, 3, 3.5, 4, and you can see what happens to the red line. It stretches out, and if I make it really small, then it gets it smaller. So there's 0.5. It's half as tall as the blue one. It goes up half as high. At least that peak does, and the valley does. And then 1, 1.5, 2. The peak of the red one is twice as high as the peak of the blue one. So that's the effect if we go that direction. And you should probably write that down, that when B changes in the equation, it has the same effect you would expect it to have in a graph, that if B is big, then the graph goes up high. And if B is small, the graph doesn't go up as high. If I fiddle here with A, let me move B back to kind of a normal place. If I fiddle with A right now is at 2.3, and you can already see that the red is stretched out further than the blue one is. So if I make A bigger, we can see the red line stretching out even further in a horizontal direction. And as I decrease A, 1.3, 0.8, and now it's smaller, it's skinnier than the blue one. So you can see that multiplying by A also has the same effect as multiplying B, but just in the opposite direction. So again, here's how this thing changes. We just want to identify what A and B happen to be. A ends up being inside the parentheses with X, and B is over here. So when we actually do the equation, we end up multiplying the whole right side by whatever B was. In fact, if we're going to change the graph, here's basically what's happening. Each point on the graph gets mapped onto a new point by going through whatever that scale change is. So A, this would double everything in that direction and triple everything in the y direction, because A goes with X and B goes with Y. Each X is multiplied by 2, and each Y would be multiplied by 3, and then it gets mapped onto a new place on the graph. So you saw how that worked on the slider. Up here you can see here I got a big number for A, and I only have a number of 1 for B. So it didn't change it at all in this direction. Horizontally it's the same height, but horizontally it's much more stretched out, or what they call dilated, in that direction. So yeah, here's our original thing again, x cubed minus 4x. And I'm going to scroll through several, and you're just going to see what the effect was. The green equation, F2, is when I've done something to it. And in this case, B was 3. If I divide both sides by 3, it would have been y, or f2, over 3. So the effect here, multiply both sides by 3, and I get a really tall graph, but the x-points, the intercepts, at least didn't change at all. Here's another one where green is my original, x cubed minus 4x, and red is my new one. And look what I've done. It would have been y times 5, and then when I move it over to the other side, it's the x equation stuff divided by 5. And of course, that makes sense that you plug in your x, you do your math, and then you shrink it down by a factor of 5. So this green one is 5 times as tall as this red one is. Here's another one. Green, still my original equation. And now the red one, I have changed the x. I've replaced x with x over 1/3, which I'm going to write as 3 times x. X divided by 1 divided by 3 is 3 times x. So in both places where there were x's, both here and here, I've replaced it with a equals 1/3. Now the effect here, you can see it goes 3 times x. Well, there's my original, and this shrinks everything down. This one's out here, and now it's been shrunken in here. And in effect, it's like it gets to the point that the original one did 3 times as fast. It gets there in 1/3 of the time that this one took to get out here. The effect, as far as picture goes, is to shrink everything horizontally. Okay, let me show you some more. There's another one. Now this one's weird because what's changed? Well, maybe we took 4x squared and we divide the x part by 3. And look at the effect. Well, it is, kind of wide, right? This one, though, is negative 3x squared. That's where we've changed something in the y direction. And it flips it, first of all. It's upside down because now it's negative. And 3, well, it's skinny. It's like it's getting to its 0.3 times as fast. The effect, that's what you kind of want to figure out. What did I do here to change my original equation, which now this time is in red, and I've adjusted it. I've replaced x with x over 2, and it's stretched out twice as long in the horizontal direction. This works for all different shapes of graphs. I'll show you this. Let's take a parabola, and then it's of the form a times x squared. So this is like y over something, and then that something's been moved to the other side. So as I move this point up, it says that a becomes 2, and that indicates a vertical stretch. Go even further, stretches even more when I make a 3. And I can go back down and put it back where it started from at 1. And I can go this way, and I can shrink it down. 1/4. Okay, it widens the parabola. And then if I keep going, I'm going to get a reflection. And this is where the a value is a negative. And now it's a negative, and it's stretched in that direction by making it bigger. If I take that basic parabola again, and I look at a variety of points along that line here, and I move that point, I'm changing a to another value. And all the points, they follow along. Every x squared increases by that same factor. I can shrink it too. All those points, then they shrink down to a smaller factor when a becomes a very small number. Actually, technically, that's the y part that's changing. I'm moving it vertically. I'm not moving it horizontally here, and that's the way that what we call a dilation in that direction with a parabola. But it doesn't matter what the shape is. Any of our parent functions will work this way. We can take that point and we can change the value of a here in front of the problem with the x, and it will dilate or stretch that by a factor of 2 or 3 or 4. And all the values, then they stretch accordingly. I plug in a 4, I get a 16 this time. I plug in a 3, I get a 12. That's 4 times as big as that number there. So it doesn't matter what kind of graph. That's why this theorem is pretty good stuff, because it applies to all kinds of these pictures. Okay, it can be square root function, and when I change the number that's in the front, which affects things in the y direction, it stretches it, or it can shrink it. So that's the basic idea here. And again, I showed you a whole bunch of examples of the stretching effect, both horizontally and vertically. This is the rule for changes to the graph. You figure out what A and B happen to be, and that original point just gets mapped onto a new point by multiplying the x by A, multiplying the y by B. If we were to do this with the equation, there's my x cubed minus 4, we're going to replace y with y over b, and then that b is going to move to the other side and be multiply the entire other side by that value. And x gets replaced with x over a, and that will stay inside the parentheses. If it's cubed, it's x over a that gets cubed, and you'll see the effect in the horizontal direction as you change the a. You'll see the change in the vertical direction as you adjust that value for b. So I'll go back to the original thing one more time, and you can see this again. I'll start by just changing the a value, and look at the equation. I'm changing the x over some number. In this case right now it's at 3.8, and here's my originals in blue, and then I'm going to change this back and pull it back toward 1 to get it closer to the original problem. This is 0.8. X gets replaced by x over 0.8. X is being replaced by x over 1.3. X is replaced with x over 2.3, and you can see then as I make that a number bigger, it stretches it out horizontally more and more. That's the effect. Okay, I'll put it back close to 1, and I'll go over here and I'll change the b value. That's the number that was right by that we replaced y with y over b. So this would be y over 0.8, or no, y over 1, y over 2.5, y over 3, and you can see the numbers, they get really big really fast. And then I can shrink it back down and make it y over 0.5, y over 4. Oop, I'll go back to 0.5. I like the 0.5. There we go. It's half as high. Everything else is the same, but it stretches it in the y direction in the way that coincides with the value for b that I replace y with in the equation. Replace y with y over b, and replace x with x over a, and you can see the effect. So play around with that. All the pictures are gonna change as you change a and b. Yeah, it's pretty straightforward as far as the rule goes for scale change. The effect on the picture seems to not match all the time, but when you change the b, it does exactly what you think it should. When b gets bigger, the graph stretches longer, and when you adjust a in your equation, well, then it goes the other direction. And again, I usually think of it like the graph gets to its point faster if the number gets bigger. The point gets to that the picture value where it would have been on the original one. It gets there slower if the number gets smaller. Hopefully that's enough for you to get through your problems. It should be up on the board, and then if you want to, you can read through the lesson again to kind of get to fill in some of the cracks there. All right, we'll see you later.